So in the last class, we have seen the code for producer, code for consumer, and a shared variables. Okay, shared code that. So in producer, there are three variables. In shared memory, there are three variables: in, out, and count. Okay, so these three are three variables that are used by producer and consumer, where in is a variable that is exclusively used by producer process, out is a variable that is exclusively used by consumer process, but both producer and consumer using the value count, using the variable count. Okay, and this particular count is used by both producer and consumer. That is how they are using. Producer is changing the value of count by count plus 1. Consumer is changing the value of count by count minus minus. Okay, so this is the only variable that is used by both producer and consumer. But this particular count plus plus and count minus minus, it appears that a single statement in high level language. But if you see this one, we can write count plus plus as count plus 1. Okay, and count minus minus as count is equals to count minus 1. Okay, so when we convert this count equal to count plus 1 and count equal to count minus 1 in assembly language, it will be divided into three statements: t0, t1, t2. That is t0, first we need to move the initial value of count to r1. Okay, that is move initial value of count to r1, so that r1 equal to 5. Then we'll increment the value of r1, so it will become r1 equal to 6. Now we'll copy the modified value of r1 to counter, so that r1 equal to 6 and count is also changed to 6. Okay, similarly here also, if count value equal to 5, or otherwise now count value equal to 6, let us take count equal to 6. Then first move count value to r2, so that r2 is equals to 6. Then decrement the count value, so that r2 will become 5. Now whatever the modified value of r2 will be there, we are moving on to counter, so that count value will become 5 and r2 will also become 5. Okay, so after an increment and decrement, after increment and decrement, the count value will be the same value of previous one. So 5, after incrementing it will become 6, after decrementing again it will become 5. Okay, one increment and one decrement. Increment is done by producer process and decrements are done by consumer process. Okay, now there is a problem here. Okay, if this is a variable that is shared by both producer and consumer, now let us take this one. If we execute this one in separate producer, all the statements of count plus plus, okay, all the statements of count minus minus will get the same value. Here the count value will be incremented by 6. Initially 5, it is incremented by 6, and here it is decremented by 1, so it will be 5 only. So at the last the count value will become 5. But let's see a concurrent execution or interleaved execution where we are implementing a time quanta. Okay, that is because all the modern operating systems are time sharing systems. So assume that at one particular time quanta it executes only two statements. That is, if one time quanta it executes t0 and t1, the producer process, t0 and t1. In the other time quanta it executes t3 and t4. Okay, then it will come to process p2, p, that is producer, it executes t2 because there is only one statement, it will execute it. Then it will execute t5. Now let's see whether the count value is same as the previous one, this one, or not. Let's see here. I will write r1 and count. Okay, so what is the count value initially? 5. Okay, count value initially is 5. I will write here count equal to 5. So after one increment and decrement, we'll again get the value 5 only. But let's see whether we'll get it or not. So on time quanta 1, tq1, let us take, it will execute t0 and t1 of producer process. So what is count value 5. So 5 will be stored into R1, C equal to 5, R1 equal to 5. Then we will increment the value of R1. So R1 will become 6. But what is the value of count? 5 only. Okay. Now here the time quanta expires. It will move to next time quanta 2. It will execute consumer process. So time quanta 2. So here what is the count value initially? It is not changed. So count equal to 5. So R2 is equals to 5. Okay, C equal to 5 because C counter value will be stored onto R2. Now R2 is decremented by 1, so R2 equal to 4, but what is the count value? 5. Count is not changed. Now the time quanta expires, so again it will go to producer process and executes this one. So what is the count value? What is the value of R1? R1 equal to 6. So R1 equal to 6 will be copied to count. So count value will become 6. Then after this one, consumer will be executed because there are no statements of producer left. So it will go to consumer and execute T5. So if you take this one, what is the value of R2? 4. Okay. Now this particular R2 value 4 is copied to counter. So the value of counter equal to 4. See, this is just replacing the value. Okay. Now look at here. After one increment, and after one decrement the value should be 5, but here the final value of counter equal to 4, which is not correct. Okay, the correct value is 5. Do we get 4? 5? No, we are not getting 4 because we are executing interleaving or concurrent execution of process P producer and process consumer. Okay, if we execute all the statements of count in assembly level language and all the statements of count plus plus and count minus minus, we are getting correct value. But if any one of the value, any one of the statements that we changed, okay, it is not executed completely. Is it executed completely? No, two statements are executed, then this statement is not executed by producer and these two executed by consumer and this statement is not executed by consumer. So before this statement is executed, we are starting executing count value. This leads to the problem. Okay, this problem is called producer consumer problem, which is also called synchronization problem, which is also called critical section problem. Okay, so it is called producer consumer problem, synchronization problem, or critical section problem. This problem comes when we execute the statements in assembly level language. One higher level language statements is divided into multiple assembly level languages where we execute concurrently, that is producer and consumer processes will execute concurrently by interleaving this particular steps. Okay, so what we need to make sure that once, because this particular counter, why this problem occurred? Because of shared variable here. Okay, this problem will not occur when we execute in or out, because in is a variable that is modified by only producer, out is a variable that is modified by only consumer. The problem comes only with count because count is a variable which is modified by both producer and consumer. So we need to take care, okay, while we executing the count. Okay, now here the count is a variable, we'll call it as a critical section variable, okay, or critical section code. Okay, or the area we will call it as the critical region. The memory location of count we will call it as critical region. So in order to avoid this particular critical section problem, there are some solutions and requirements that are provided. Okay, okay, so critical section, when multiple processes are executing a shared variable, multiple processes, assume that P0, P1, P2, so on up to Pn, if they are executing a shared variable like count, we need to make sure that, okay, This, when one process is executing, that is if p0 is modifying the variable count, okay, we need to make sure that no other process will modify the value of shared variable. Okay, so we need to use some mechanisms here. So let's divide. So critical section divides this entire program or code into three parts. Okay, so first one, critical section code. Okay, then non-critical section code. Non-critical section code, we'll call it as reminder section. Okay, so this is non-critical section code. Okay, so let's see producer consumer. Except this particular line, this particular line is our critical section code for producer, and this particular line is a critical section code for consumer. Okay, and everything will be your reminder section. Everything before this one and after this one will be our reminder section. Okay, so before entering into critical section, that is before modifying the value of count, okay, the each process has to satisfy this particular entry section. Okay, so entry section, critical section, and exit section. Okay, so the process which satisfies the conditions of entry section, here we'll provide some conditions, and if this particular condition is satisfied, then only the process will go to critical section and modify or execute the critical section code. Once the critical section code is executed by one process, then it will come out and execute the exit section so that other processes can execute the critical section. Okay, so there are three requirements will that has to satisfy by satisfied by each process. So the each process, that there are three requirements. Okay, so first one will be mutual exclusion. Okay, so what is mutual exclusion? When multiple processes are trying to execute a critical section code. Okay, trying to execute critical section code. See, this condition is called race condition, when multiple processes wants to execute critical section. Okay, so here, when, what is mean by mutual exclusion? When one process, suppose that px is a process that acts currently executing critical section, then no other process other than px can execute critical section code. That is, no other process will modify the value of count until and unless this particular px will execute all the statements of that particular count in assembly language. Okay, so once, that means mutual exclusion gives you guarantee that there is only one process that is currently executing critical section code. Okay, so next, progress. What is mean by progress? When there are multiple processes that wants to execute critical section, assume that px, py, pz. Okay, so out of these three, only px and py wants to execute critical section code, and pz is not interested in critical section code. So this particular progress will determine either px or py will enter into critical section, that execute critical section next. So progress determines which process will execute the critical section code next. The process which doesn't want to execute critical section, progress doesn't take count. Okay, then once there are multiple processes which are requested for executing critical section. Okay, the process will be given certain amount of time, or process will be given certain waiting time. Okay, so this waiting time, that means if p0 is executing, then P1 is also wants to execute critical sections, and P2 also wants to execute critical sections. So on, all the processes wants to execute critical section. There should be a limited time period so that this particular process turn, okay, waiting process turn will come. The waiting time should be limited. It cannot be uh, infinite waiting time. Infinite waiting time. Okay, the waiting time of process which wants to execute critical section should be limited. Bounded means limited. Okay, so all these three conditions must be satisfied by processes.